Hello, everybody. John MELBYE with Become Demand Driven. And today I want to run through a series of slides that introduce you to the demand-driven MRP or material requirements planning methodology. I first came across the demand-driven methodology in 2012 at a conference, and it struck me as interesting, and I decided to follow it a little bit. And in 2014, I got my first certification, and I've been teaching the demand-driven planner class since February of 2017. DDMRP is a tool set that changes the way we approach our inventory management and leads all the way up into our supply chain management. So let's get started. What is traditional material requirements planning? Joe Orlicke wrote the book, 1975, and the idea was that we were going to be able to run our supply chains using time phase planning, level by level bill of material explosion, and dependent demand planning. The benefits were going to be component synchronization, reduction in inventory, and improved priorities. Now, let's unpack a couple of those things. Dependent demand planning. If we have a demand for an end item, and that end item requires all of its components, MRP is what allowed us to say, I need to produce a bicycle, and therefore I need all of these components, and here's when I need them. That's the time phase planning. All of the components will come in exactly when we need them. That's the component synchronization. We will reduce inventory because we're not guessing anymore, and we'll improve priorities because we'll have a due date for each of those items, and we'll know exactly what needs to happen precisely when. And Joe was quoted here. I'll just read that last little bit. I, for one, have no doubt whatever that it will be the way of life in the future. Well, of course, MRP did become the way of life for planning. It was conceived in the 1950s, put into computer code in the 1960s, commercialized in the 70s, and by 1990, most manufacturers of even modest scale had some form of an MRP system. But something isn't right. Most planners and buyers today mistrust their planning tools. So they take the output from the planning tool that was created and they use spreadsheets to fix it, to tweak it, to apply their business intelligence and actually change the output from this beautiful system that is supposed to have all these benefits. Of course, spreadsheets have their own problems, limited in capability and scalability. And of course, most of us don't like to tell others how we created our spreadsheet. Therefore, it's hard to transfer to other people. They also likely to have errors. I know none of my spreadsheets ever had errors, but other people I've heard sometimes make mistakes. And let's look at what's changed in the world. 1965 to today, we've got more supply chain complexity. Our product life cycles are shorter. Customers are not willing to wait. The complexity and the customization and the product variety are all high. We have long lead time parts. We have low forecast accuracy. We have pressure to reduce inventory, and transactional friction is low, which means it's much easier to make a purchase. Think about one click, and it's much easier to find suppliers and find other people who make the same product you do. So the supply chains look very different from when MRP was created. But the planning rules in conventional MRP haven't really changed since the 1960s. MRP still functions the same as it did 50 years ago. And what that means for us is this changed environment requires a different way to think. So we've got longer supply chains while the customer is willing to wait less. And there's a huge gap between how long it would take us if we waited for the customer order, how long it would take us to actually deliver to the customer. There's a huge gap there. And that means that we have to hold inventory somewhere at some strategic point in either in order to keep or to grow sales. It also means that the planning horizons are more remote from the actual demand, so we need a longer range forecast. There's more products with shorter lifespans, and often they're using common components and resources. It means that managing stock positions effectively is something that we have to do in order to effectively manage our capital and our resources. And it also means that the detailed item level forecasting is much more difficult. And we know our 3 rules of forecasting. Forecasts start out wrong. The longer the range, the more wrong they are. And the more detailed they need to be, the more wrong they will be. So conventional MRP requires or depends on those forecasts to be correct, and yet the situation we're living in is making them less accurate. Well, let's start here. I think we can all agree that there's 2 universal points of inventory. Point A, where we have too little, and point B, where we have too much. And it kind of stands to reason, maybe it's fairly obvious. Where do we want our inventory to be? Well, we want it to be right in between those 2 points. And so between those 2 points, there is some location that is the optimal range of inventory that we need to try and maintain. But most companies exhibit what we call the bimodal distribution. We either have inventory where we don't have enough, or we have too much, and we have almost no inventory in that optimal range. And it's important to note that this is by design of the MRP system, because when MRP was created, we wanted to have no inventory left over. It was basically the perfect make-to-order calculator, not a way to manage inventory. And with every MRP run, we go back and forth, and inventory moves from too little to too much, and vice versa, because of all the other things that are changing in that same time. And 90% of companies report this issue. The 3 bottom line effects is we have chronic shortages. At the very same time, we have excessive inventory, and we have high expedite expenses and other wastes like overtime when we don't need it, and causing us to run out of parts, which causes us to run more overtime, et cetera, et cetera. But the real problem, these are the symptoms. The real problem is that we have something called the bullwhip effect. And the bullwhip effect, the definition is clear. I think most of us have heard of the bullwhip effect. A small change in one end of the supply chain will create a huge change in the other end of the supply chain. Due to the serial nature of communicating and just the inherent transportation delays of moving product, we end up with the bullwhip effect. And what we're really talking about is the transference and amplification of variability in both directions. So we have the demand signal distortion moving one way, and we have the supply continuity variability running the other way. And what we can see is that as we move from one end to the other, that variability keeps growing, and it just keeps getting worse the further we move. The more parts we have, the worse the effect. And the true solution to fixing this has to stop the distortion in both directions, both the demand and the supply distortion. So let's start this little puzzle. We have demand signal distortion, and we have supply continuity variability. And material, the result of those 2 variabilities is, or those 2 distortions, is that material is not ready at the needed time. So why do we have demand signal distortion? Multiple reasons. We have signals with known error that we're using. We have latent signals. We have oversimplified signals and changing and conflicting signals. So if we fix the demand signal distortion, have we solved the bullwhip? No, we have not, because we still have that supply variability to deal with. And MRP plans will never properly synchronize because we're expecting everything to happen exactly as the plan says. And the longer the time period we have, we know that precise planning is not going to be real. So I want to introduce demand-driven material requirements planning. It is a method to model, plan, and manage supply chains with the intent to protect and promote flow of relevant information and materials. We use strategic decoupling points, which is usually an inventory balance, to drive the supply order generation. In other words, creating the purchase or the manufacturing orders, and then managing, so the expediting or the changes in those orders throughout the supply chain. There's a lot in that. Model, plan, and manage supply chains. Model sounds like kind of a simulation world. The planning part is MRP. The P of MRP stands for planning. And manage. And so what we've done is we've separated the planning side of our business and the execution side. So we're not using, when we create a purchase order, we're not immediately expediting in every scenario. First came out in 2011 by the Demand Driven Institute. After 15 years of research and application, it is built on the pillars of material requirements planning, distribution requirements planning, lean, theory of constraints, Six Sigma, and 4 bits of innovation. And what we end up with is this mantra of position, protect, and pull. There's 5 components in DDMRP: position, protect, and pull. Ends up being strategic decoupling, where we determine where we're going to hold inventory. The buffer profiles and levels, once we determine where we're going to hold inventory, we need to figure out how much we're going to hold there. And then the dynamic adjustments means that those inventory buffers have to adjust as our world changes around us. We need to follow the demand-driven planning methodology, and we end up with visible and collaborative execution, where we have everyone understanding or able to easily understand what is our intent and where are our pain points at the moment. Now, let's go back to our core problem here, where we have distortions to relevant information and distortions to our supply signals. Why do we use latent signals? Well, often people will talk about weekly buckets or monthly buckets. We don't say, okay, we need to produce every day this much. We say, hey, we need 500 this week, and we incorporate that into our planning. But we don't build it in the week, we build it every day, and so it distorts our signals a little bit. Sometimes we use oversimplified signals, which means we've used phantom or pseudo parts where we don't transact, so we know we've made the conversion, but we don't do a transaction, which means we don't have the same information as if we did a transaction. And what do we get with the changing and conflicting signals, the oversimplified signals from a flattened bill of materials, and those weekly buckets? We end up with what we call system nervousness. And those of you in supply chain know that we get exception reports where we're supposed to pull in and push out, constantly moving the due dates and the quantities of items because of all these things. And we call that system nervousness. Why? Why do we have system nervousness? Because we have to put in the actual number once it becomes known. Why? Ties us back to our signals with known errors. We're using forecasts to determine our actions today. So MRP is based on forecasts driving us to place our orders for our components, for example. Why is that? Because the cumulative manufacturing lead time and the procurement times are much longer than the customer is willing to wait. So we have to put something in MRP. And this was the tool we had. This is the only way we could look at it because the lead times have extended and the customer wait time or expectations is much less. So up until now, it hasn't been wrong to do this. This was the only tool we had. And why is this? Because MRP treats everything as dependent. Everything is connected to everything else. Now, let's go up and answer this question. Why are MRP plans never properly synchronized? Because supply variability transference causes delay accumulation across the dependent networks. And delays accumulate, gains do not. Why do we have that accumulation and that delay? Because MRP plans, the timing and the quantity are all built using dependencies. Now, let's talk about the first step of DDMRP is position. We need to strategically decouple. And decoupling means we're disconnecting the rate of supply from the rate of use. We're putting a break in there. How do we do that? Here's your introduction to the demand DDMRP buffer symbol, this little bucket with red, yellow, and green in it. If we put a bucket of inventory or a position of inventory in between the subassembler and the component manufacturer, we don't eliminate variability, but we stop the transfer and amplification of variability in both directions. Both the demand signal distortion stops and restarts variability, and the supply continuity variability transference and amplification stops and restarts. So we see the beginning of the direction of the beginning of the solution by putting inventory in places where we need to disconnect the rate of supply from the rate of demand. And we know about decoupling points in our regular lives because most of us, at least in the US, have a water heater that allows us to use hot water on demand and to use more hot water or less hot water and not run out of hot water for the most part. We also live in towns where there's a water tower, and that water tower allows everybody in the town to turn on their water at the same time, and everybody still gets water. So we disconnect the rate of supply from the rate of demand with these decoupling points. The other thing we gain here is that our planning horizons shorten and we have different and shorter lead times. How is that? Well, if I know I have inventory here, I only need to plan this section. I don't, and the things that need to align and happen precisely is a shorter window of time versus the whole length of time from end item assembler all the way back to the foundry. So my planning horizons shorten and I end up with lead times, knowing I have inventory here. My lead time to the customer means I only need to consider back to this point, not all the way back to the foundry when I'm creating the lead times. There's 6 different criteria for where we're going to place inventory, because if we're going to have strategic inventory positioning, then we need to make a strategic decision. Why do I keep inventory at this place? And here's the 6 things. I'll go through them relatively quickly. How long is the customer willing to wait is the first thing. If the customer is willing to wait 1 day, you probably need inventory at the end item. If they're willing to wait 10 days or 20 days, then you can put it somewhere, maybe all the way back to raw materials. Market potential lead time. If we have a 10-day lead time and a 5-day lead time would create either additional business or an increase in price, then maybe we need to make that buffer somewhere 5 days that allows a 5-day window or lead time to the customer. The sales order visibility horizon has to do with when we become aware of the sales orders. Do the customers give us plenty of time to produce this, or are they constantly calling with a shorter than expected lead time? Our variability, right? We have demand variability that impacts closer to the end item, and we have supply variability that is more impactful at the raw material side. And then in between, we may have some disruptions as well, but we just talk about variability by part number. Inventory leverage and flexibility. If we have a component that goes into almost everything we make, even though it might be a low cost or long lead time or short lead time, whatever the concept, we need to make sure we have that inventory because it goes into everything we make. And then the protection of a critical operation. If we have an assembly cell or a machine that has to run 24/7, then we have to have inventory to make sure it doesn't shut down because we ran out of inventory. And the way this position works, and the difference if we compare traditional MRP where everything is coupled and we have an 8-week lead time, to the DDMRP function where we've placed buffers in such a way that says we can have a lead time to the customer of 1 week because we know we have this inventory, and then we have a lead time of 3 weeks between purchase parts and our own operation, and then we have a 4-week purchase part, and each buffer is separately managed, and that allows the management to happen within those shorter windows of time. And it seems obvious again to me that managing a 1-week lead time, it's easier to get precision to line up in that 1 week than it is to get precision to line up over an 8-week period. MRP was never designed to manage inventory. It wasn't designed to decouple. It was designed to make everything dependent, which means everything has to work exactly according to plan. And the plan was set 8 weeks ago in this case. And the chances that my plan for an entire 8-week window is going to hit exactly is almost no chance. Okay, we've determined where we're going to place inventory. Now we need to size how much inventory are we going to keep in those locations. The interesting part about the DDMRP buffer is that it's a 3-zone buffer, and the 3 zones, each zone has its purpose and its equation for calculating, and they are separately managed. The green zone has to do with how much we're going to order and when we're going to order and how often we're going to order. So order size and frequency. The yellow zone is our primary coverage, or we call it cycle stock. How much am I going to use on average over the lead time of the part? And then the red zone is the safety embedded in the buffer. And we use things that we know that are not unusual to us, like lead time, minimum order quantity, the location for distributed parts, and an average daily usage. The item type, is it purchased, manufactured, finished item? And then lead time category and variability category, those are a little bit new, but not unknown, because if we know the lead time, we can say whether it's a long lead time or a short lead time. And we kind of know the variability. We have our feeling, and we can calculate variability to say, is it a high or a medium or a low variability? And that these items give us the zone and buffer levels for each part. As an example, when we look at this part, we're not going to complicate things with a demand adjustment factor yet. We have an average daily usage of 17, lead time of 21, order multiple of 300. It is a buffer, is a purchase part. It has a long lead time and it has high variability. So we've coded that into the system. And based on that, our 3 different zones get calculated at 300 for the green, 357 for the yellow, and 233 for the red. MRP, again, not designed to manage stock positions. It's the perfect make to order calculator. And before I jump ahead here, so MRP never doesn't manage stock locations. MRP is designed to net to 0. DDMRP for the strategic buffers never nets to 0. And before I move ahead, a caution, a little note of caution. The buffer of this size, this is not the total bucket of inventory we hope to have. The inventory level will sit somewhere here above the red and partway up into the yellow. That's our expected on-hand inventory. And it's very similar to a Kanban situation where you might have 10 cards of 100 parts or 100 boxes each, which would mean 1,000, an inventory of 1,000. If everything shuts off, all the demand shuts off, and all the suppliers keep delivering until those cards are filled up, you would have 1,000. But that's not your intent. There will always be some on order, there will always be some in production, and there will be some on the shelf. So similarly, this is the bucket. If everything shuts off, if we have demand just drops and the suppliers keep shipping, our maximum exposure, just like a Kanban system, would be the total of this bucket. And it's something that trips people up right off the bat. If we don't say that, we think this is the amount of inventory I'm expected to have, which is 890 parts for an average usage of 17, seems a little bit nuts. So understand that that's not your bucket of inventory. That's your planning buffer that we will use to make calculations from. The buffer is not safety stock. It's not duct tape. It's not a fire alarm. Like traditional MRP, when you hit safety stock, there's a fire alarm that happens. DDMRP is more like a firewall. Again, separating that rate of use from the rate of supply. The third step is dynamic adjustments. We are going to talk about recalculated adjustments. So the automatic recalculated, if the average daily usage changes, if the lead time gets changed in the system, if an MOQ drops in, it automatically implements in the buffer. And we have something that we don't go into detail here called demand adjustment factors, where we can intentionally flex the buffer in case of seasonality or sales promotions or different planned events. We can intentionally flex the buffer to be able to be prepared for those things instead of our traditional life where we're often reactive. Conventional and safety stock and reorder point positions are usually static, and they only change when somebody realizes there's a problem. There's some cases where they are dynamic, but still, because it's still a determination, like a line you've crossed. Safety stock is essentially the new zero. So you've just reset from 0 to whatever number you put in safety stock, but the problem didn't change. When you hit safety stock or you hit 0, MRP reacts exactly the same. Total panic, we have to have these parts right now, and forces you to expedite unless you manually do kind of a self-intervention and say, well, I don't need to expedite. But that's outside the system again. We're adjusting and adapting from this complex system that's called traditional MRP. We take that information and then we have to do all kinds of work to figure out what we really need to do. And that hasn't changed since the beginning of MRP. All right, number 4, the fourth step. We're trying to work with a better demand signal than the forecast. In the conventional master production schedule, MRP planning world, the planned orders are based on the forecasts, driving us back over a longer planning horizon, forcing us to have longer and forcing us to work to have longer forecasts that are more accurate, which is harder and harder to do. DDMRP uses qualified sales orders. And in reality, we also use forecasts. We just use them differently. We use them to determine our average daily usage. The sales order is highly accurate. The planned order is highly inaccurate. And so we start with a more relevant supply order generation equation. So this is one of the innovations of DDMRP. It's called the net flow equation. Questions that every planner and buyer cares about each day. What is on its way to me? What do I already have in stock that I can use? What demand do I need to fulfill immediately? And what future demand is relevant? So every day we apply the net flow equation. And the net flow equation on hand plus the open orders minus the qualified sales order demand. There's a little bit in that qualified sales order demand that we don't cover in this section, but on hand plus open supply or on order minus the qualified sales order demand. We compare that to our planning buffer. That gives us our net flow position. If we are in the yellow or red, we order up to the top of the buffer. So you can see this is how we answer the question in a process. How much do I order and when do I order it? How much from the net flow position to the top of green if I'm in the yellow or red, and when my net flow breaks into the yellow or the red, that's when I place my order. So let's go through a 17-day kind of simulation here. We've got a sample part figured out, average daily usage of 10, lead time, replenishment lead time of 7 days. So that's a medium lead time. That's a medium variability part. We've got an order spike horizon. So we're going to look out 7 days because we have a 7-day lead time. And we're going to look for items that are above 50% of my red zone. So orders or daily buckets of orders that add up to more than 26. So as time progresses, we're going to see today is our buffer. And the supply orders are going to move in from one side. The sales orders are going to ship out from the other. And so as I move to the next day, those orders are going to come in and we will evaluate our situation accordingly. So on day one, we have our buffer. We have some items on hand. We have 65 on hand to start. We have 72 on order. That's the sum of 37 and 35. And we have a sales order demand of 10. And we look forward and we see nothing over our spike threshold. So on hand plus on order minus the sales demand means we have 127 as our net flow. We are in the green, so we order nothing today. Day two, we have a spike out on the horizon. So we have on hand of 55. We have on order still of 72. And our sales order demand is 18, which is due today, any past due, and the qualified spike of 30. So there's no past due. 18 plus the spike of 30 gives us a sales order demand of 48, which means our net flow is 79. That puts it in the yellow, which means we're going to place an order up to the top of green or up to the top of the buffer. Today's order recommendation is 78. Day three, we've placed our order for 78. What else happened? We had 35 pieces that were being delivered. So at the beginning of day two, it's still on order, but by the end of day two, it has arrived. So we add 35 minus our 18 that we shipped out, and our on hand is at 72. We now have an on order of 115, which is the sum of those two orders, and our sales order demand is 17, which is due today. We have no past due, plus the spike that is still within our horizon. So 47 becomes our sales order demand, but net flow is in the green still, so today we are not going to order. Day four, again, 55 on hand, 115 on order, sales order demand of 6 plus the 30 that is the spike, so 36. We get a net flow at 134, still in the green. We don't need to order. Day five, 49 on hand, 115 on order, 35 is our sales order demand, 5 plus the spike. But our net flow is still in the green, so we're not going to place an order today. Day six, our on hand is getting down into the red from a planning perspective. So 44, still on order at 115, sales order demand of 39 because we have 9 due today and our spike of 30. Our net flow is in the yellow, so we're going to place an order for 37. And then today, 37 come in, 9 ship out. So our on hand jumps on day 7 to 72. Our on order still 115. Sales order demand at 40 because we're shipping 10 plus we have the spike. Our net flow is 147. So in the green, we won't place an order today. Day 8, net flow still 147 in the green, and we can go through each of the items. But what's happening today is we're going to ship that spike, and we have on hand 62, so we have plenty on hand to ship the spike. Next day, our on hand drops to 32, but the 78 that we ordered, because we saw the spike at the front of the lead time for that part, we have 78 coming in, so we're not quite in trouble. If you're me, I might be placing a call to that supplier, making sure those 78 are on their way and on track for delivery. But if everything is happening as it's laid out here, and there's no reason, right? We didn't expedite the 78. We just ordered with the lead time that they told us. If that has held, these should come in today, no problem, which means on day 10, that has come in. I have 105 on hand, 37 on order, and my sales order demand of 6 because I have no spikes into the future. Net flow in the green, I do not place an order. Day 11, again, net flow in the green, I do not place an order. My on hand is 99, and my sales order demand is 9. Day 12, I've dropped, my net flow has dropped to 117, which means I order up to the top of green because I'm in yellow. So I'm going to place an order for 40. Day 13, you see my order for 40 came in here. I still have no spikes that I need to worry about. I'm in the green with my net flow, so I don't need to place an order. Day 14, I'm still in the green with my net flow, so no order is needed. Day 15, I've dropped into the yellow on my net flow, so I'm going to order up to the top of green, which is an order of 37. Day 16, I've got 147 in my net flow, still in the green, no orders today. Day 17, no orders today because my net flow is still in the green. So you can kind of see how the days progresses if you're a buyer or a planner, what kinds of things you're looking at. And one of the cool things about DDMRP is we can now look at history and see how we performed. My net flow, when I break into the yellow, I order and get myself into the green. I break into the yellow, I place an order. I break into the yellow, I place an order. Pretty straightforward, and something you can put into a process now to determine how much and when you're going to place an order. My on hand in the black here, that line has followed, and we had one spot where we got a little bit low, but then our order of 78 came in and we raised our inventory back up. You can see the open supply on the graph, and you can see our demand on the graph as well. Average on hand inventory is 71.6. And let's see what that looks like. Okay, average was 71.6, but boy, this distribution of on-hand inventory sure looks a lot like that inventory curve right in between too little and too much, doesn't it? And so we've got some outliers. We dropped below where we wanted to be, and maybe we're above where we wanted to be. So that's our continuous improvement activity, is find out why those happen, try and solve that, and we squeeze that together, and we get more items in that, more days where our on-hand inventory is in that optimal range. And if we compare our net flow to our on-hand, we really see it doesn't line up for any reason. But we can learn from our net flow. We break into the yellow, we place an order. From our on-hand, our execution, when we get too low, we may need to expedite, but it gives us a signal. When I get too low, I know that maybe I have to do something about it. All right, the decoupled explosion is the second innovation that we talk about here. Traditionally, explosion is different, right? The yellow components here are the buffered components. And when the net flow position causes us to release an order, that's when the explosion starts. And it stops at the next stop position, no matter what. It doesn't keep exploding. And each one that breaks into the rebuild zone, that's when the explosion restarts. Now, how is that different from traditional MRP? Traditional MRP, if there's a change to that end item, everything else in the bill of materials has to also change. And that change can be timing, so due date, or the quantity. And everything else has to change. And you can imagine the chaos that ensues in my exception report when it tells me every day, okay, push this one out, pull this one in, keep moving things around, and it drives everyone nuts. DDMRP says, only cause that chaos in between the buffered components, which means it's not really that much chaos. And we can manage precision in these smaller windows. But in between the decoupling points, DDMRP and MRP work exactly the same. They both try to net to zero, and they both expect precision to happen. That's why we call it DDMRP, because MRP is still inside of DDMRP. The fifth is the execution side. And what we're doing really is we're questioning priority by due date. If you set a due date today for 3 months into the future, it isn't very long before that due date is no longer correct, and we have to keep changing it. But if we think about priority in a buffer, we can think of it by buffer status. So here's my on-hand buffer status, tells me with this PO for this part number, I have 27% of my buffer remaining. For this one with this work order, I have 42% remaining. So if these are the parts that I have strategically decided to buffer, when I'm at 27%, now I need to execute in an expedited fashion, or at least go look at it. And in this case, I have a clear and simple prioritization. So I can decide, hey, I'm in purchasing this PO, this one's urgent, that's on my list, I'm going to get to that first. And if I'm a planner and I've got a work order, this one's urgent because it's in the red, I'm going to work on that first. And I don't have to spend a bunch of time trying to figure out what I should be working on today first, because my priorities are aligned for me. And if I look at this scenario that we face every day in the traditional world, I've got due dates set up for different parts. But if I look at my buffer status, the one due on May 14th is actually the most urgent of my manufacturing orders. So that's the one I should be doing first. Why would I produce to a due date that's going to ensure that I run out of the part that's due on May 14th? So we say goodbye to the bimodal distribution. We end up with inventory in that optimal range for those strategic buffers. And we end up with the tails of the distribution being our continuous improvement list. So we can apply our improvement tactics to continue to grow that optimal range. And we end up with happiness all around. DDMRP's proven benefits, typically we end up between 97 and 100% on-time fill rate. So the customer is happy. We compress the lead time, sometimes in excess of 80%, but let's just say we cut it in half. Wouldn't your customer be happier with a shorter lead time? We right-size the inventory, and we overall end up with a 30%, let's call it on average, 30% reduction in inventory, because we take the items that we have too much of and we finally understand what to reduce it to, and the items that we have too little of, we can stop chasing those around because we've determined what is the right size of that inventory. We essentially eliminate expedited shipping, schedule break-ins, and cross ships, and partials, which means we end up with a lowest cost total supply chain cost. And it's easy and intuitive when we think about that execution piece, where we determine not by due date, but by the amount of buffer protection that we have remaining. The book is Demand-Driven Material Requirements Planning by Patak and Smith. Version 3 is the current version. There's a Demand-Driven Planner class that will prepare you for the certification of a Demand-Driven Planner professional. And DemandDrivenInstitute.com is the authoritative website from the Demand-Driven Institute, and my website, BecomeDemandDriven.com, where there's a lot of writings, kind of analogy and metaphors to help people understand how this different planning system works. Thank you very much for joining me today, and I hope you enjoyed this video. Take care, my friends.